we're going to deal with the recursion because we're punting remove with 2 kids. And so now let's say we're in the situation. So when are we going to recurse, right? Well, we're going to recurse when we're in the situation that left and that our data doesn't equal our hash code, okay? And left and right aren't null. So if my data, data to remove. I gotta be remove dot hash code is less than data dot hash code. So that means the thing better be on the left, right? Left, right? And let's do a check that says left does not equal null, all right? Well, then what we have to do is we have to say left equals left dot remove data to remove, okay? So we're going to recurse that way, and we're going to make sure that left's going to return what I should be pointing to in my left after it's done, right? Now remember the case, and I should, now if this happens, we're going to return this because our parent better still be pointing to us after this because we're not getting removed, okay? Now let's play this game again, okay? If data to remove dot hash code is less than data and or hash code is greater, data to remove that hash code is greater than data that hash code, and right doesn't equal null, well, we better recurse to the right. So right equals right dot remove, because we know the data to remove must be to our right, and then we return this, okay? So hopefully that makes sense, right? If it's less than me and there is a left, that means if it's there, it's got to be to my left. I'm gonna send it down. I'm gonna return this, okay? And if it's right and it's got to be there, I'm gonna go right and return this. Now there is a chance that left is null or right is null, and in that case, I'm not gonna recurse, but I am still gonna return this, okay? So if we're at the end of the binary search tree and there's nothing to remove, well, our parent still needs to point to us, so we're going to return this, okay? So I think we've got it all figured out right here, for the most part, except for removing 2 children, but who knows? I mean, this stuff, I did a lot of armchair stuff right here. Okay, so let's try this. Let's see ABC, right? ABC. So 705, 703, 702, okay? And if we print it, we'll print it here. And if we run it, 702, 703, 705. Perfect, okay? And now, you might guess, we're gonna remove, oh my God, my tree, not my remove. Remove, and we're gonna say remove C from here, right? Which will be 702, okay, the far left one, and we'll see what happens. Well, I mean, let's see. So that's the 0 case. That's the 0 child case, and we'll just print it out and hope. Well, I mean, I don't know. We'll see. Not good, right? So what happened here? Well, something fishy's going on. It's almost like, so we inserted A, B, and C. Hold on. Let's say, wait, hold on. Let's do this real quickly to make sure we'll do the sanity check. So this is right. So our inserts have been right, but then if we do this, that's not correct, right? This is 702, 703, 705, 703, 705, all right? Things are not going correct. So it sounds like we're not setting something correctly. So left equals left dot remove data to remove, and then we're returning this. Okay, so If left is null, well, let's just do it. I always tell students we should debug this together. Let's just debug this together, right? We're all human. Actually, I shouldn't. Some of us shouldn't be professors, but we'll save that for another day. Okay, so all right, so we have left equals null, right equals null, data to remove that hash code equals data to remove. Okay, so if we're in the situation where we have no children, we're going to, and we need to be removed, we're going to return null. That's correct, right? Because if this needs to be removed, right, we're removing 2, 5 better point to null because 2 had no children, right? Had no heirs. Dun, 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 dun. All right, so then if left did not equal null, okay, if the thing we're gonna remove is this, and left did not equal null, okay, but right equals null, we're gonna just replace. We're gonna return left. Okay. Similarly, if left is null, but right does not equal null, and we've got this situation going on, we're going to return right. Okay, so that seems like good base cases. If data to remove .hashcode, good, is less than data.hashcode, which means this thing better be on the left-hand side, and left does not equal null, left equals left dot remove data to remove. Okay, so let's play this out. Let's play this out because that's the case we're doing right now. 5, 3, 2. Okay, and so let's play this out real quickly. All right, so 5. Then we're gonna remove 2. Let's say 5 says, well, it's not 2, so I'm going to recurse on my left. Left equals left dot remove and data to remove. Okay, so that's fair. It's just passing it along and it's saying remove data to remove, and then it's going to return this, which is right because root better point to 5 still. And then we're in 3, and 3 is going to come down here and it's not 2, so then it says, well, it's less than me, and my left does not equal null, so it's going to call that on 2, and then it's going to return this. All right, fair. And then finally, we're going to hit 2, right, and left does not equal null. Oh, I think I know my I think I know what happened here. Does anyone know what happened here? I don't think this might not be a mistake, but let's keep on going through it. Let's do the sanity check. Okay, so now we're at 3, and 3 is going to do the same thing by saying, okay, I'm going to set my left to whatever this returns, so, and then I'm going to return this. So 5 is going to point to 3 when this is done because it's returning this no matter what. 3 is going to point to whatever this recursion returns, and this recursion, since we're removing 2, should hit, and it has no children, it should hit this case right here. Okay, null, null, and then it should return null, and we should have this. So what's going on? Well, some of you might have noticed that, remember when I tried to make it look spiffy in the print, and so I made it system.out.print? One thing we might want to do is we might want to put a return carriage here because these trees are going to start running together. So how do we do that? Well, let's put a return carriage right up here. So root.print, but before we do that, we're going to go system.out.println return carriage. And now we'll see something that's probably a little more sane. All right, so that'll give us an enter before we print the tree, which is really what we want. Otherwise, we're going to get confused like this. All right, so now let's do this, and well, it looks like it worked. Okay, so we went from 702 to 702, 703, 705 to 703, 705. So it looks like we successfully removed 702. I want to play the game again now And I want to remove the thing with one child, right? So which one would that be? That would be 703. So let's do that, right? And that's B, right? Beyonce. We're not going to remove Beyonce. If we remove Beyonce from our label, that's the worst decision ever. Well, let's see what happens when we try. 703, right? And so we want 702 to point to 705, right? Essentially, what 3 should do is it should say, well, this is my one child. Here, my parent. Point to my one child. That is deep. That is like Shakespearean or something. All right, let's try it. Why don't we try it? Okay, and 702, 705. All right, so it looks like some of these situations work. We should really try one more. We should try to remove the root, okay? And make sure that's working. So if we remove the root, it should just be, so 5 is gonna return its one child, which is 3, 703, and so it should be 702 and 703. And let's try that case, okay? 702, 703. All right, so it looks like everything's going, which means it is time for the final step, which is removing a node with 2 children. If you need to get a drink of water, you need to go to the bathroom, this is the time to do it. This is the time to do it. I'll see you in the next video.